we discuss about the integrals of rational functions that are evaluated using partial fractions. So the idea is to disintegrate or to break down a rational function into several partial fractions. So for example, um, you have a polynomial over another polynomial. We're going to transform this into several partial fractions. No? So a over f of x plus b over g of x plus and so on and so forth times dx. And then we evaluate the integrals separately. So we are given a proper rational function. Proper rational function in the sense that the degree of the numerator, the degree of p must be less than the degree of the denominator. Example is x plus 3 over x squared minus 7x plus 6 dx. The degree of the numerator should be 1 degree less than the degree of the denominator for it to be a proper rational function. If you have the integral of x squared dx over x squared minus 4, this is an improper rational function because the degree of the numerator is the same as the degree of the denominator. So what we normally do is we get the quotient. The quotient of this will be 1 minus 4 over x squared minus 4. And then you integrate the quotient separate from the integral of the remainder together with the denominator. So this is the proper rational function. While this one is the quotient which you can evaluate separately. So in this particular technique of integration, involving partial fractions, we will consider 4 different cases involving the factors in the denominator of a proper rational function. Okay, so the first case is when you have distinct linear factors in the denominator. So for example, you have 3x minus 1 all over x plus 4 and 3x minus 1. The factors in the denominator are linear and distinct. No? The second case is you have repeated linear factors. So for repeated linear factors, example is 3x minus 1 over x plus 4 raised to the power of 3 and 3x minus 1 raised to the power of 2. Both factors are linear, but they are repeated because of the exponents 3 and 2. Then we will go to case 3, wherein we have distinct quadratic factors. So for example, you have 2x minus 1 all over x squared plus 4x plus 8. This is a quadratic factor, and say there is another quadratic factor, x squared plus 4. So the quadratic factors are distinct. They are not repeated. And finally, case 4 is when you have repeated quadratic factors. Say x squared plus 3x minus 1 over x squared plus 1 cubed and x squared plus 4 quantity squared. So these are the 4 cases that we will consider. Okay? So we start with case 1. So case 1, distinct linear factors. For each distinct linear factor, ax plus b, there corresponds one partial fraction of the form a all over ax plus b, where a is a constant to be determined. Okay. Hence, if a sub 1 x plus b sub 1, a sub 2 x plus b sub 2, up to a sub kx plus b sub k are distinct linear factors, then the partial fractions involved are a1 over a sub 1x plus b1, a sub 2 over a sub 2x plus b2, plus and so on and so forth, a sub k over a sub kx plus b sub k, where a1, a2, up to ak are constants to be determined. Alright? So if there are several distinct linear factors in the denominator, there are k different linear factors, there will be k partial fractions. So the integrand will be written as a sum of these k partial fractions. So let us have an example. We evaluate the integral of dx over 4 minus 3x minus x squared. Okay? Of course, there's another way of evaluating this integral, and that is by completing the denominator as a perfect square trinomial. But we will apply partial fractions in dealing with this integral. So what we do is we isolate first the integrand. So isolate the integrand. And the idea is to write this as a sum of partial fractions. So 1 over 4 minus 3x minus x squared. And observe that the denominator is factorable into 4 plus x and 1 minus x. Okay? So taking the product, 4x minus 4x is negative 3x, and x times negative x is negative x squared. So there are two linear factors, 4 plus x and 1 minus x. So the partial fractions, there will be two partial fractions, a over 4 plus x, that is the partial fraction corresponding to the factor 4 plus x, plus another constant, let us call the other constant as b, over the other linear factor 1 minus x. So we have simply broken down the radicand into a sum of two partial fractions. So the next thing to do here is to solve for the constants a and b. So we simply combine the two fractions. We'll be getting the same denominator, of course. So that will be a times 1 minus x plus b times 4 plus x. And then we can cancel both denominators. Right? So that is equivalent to 1. And then let us combine similar terms. So negative a plus b quantity times x. No? So we have negative ax and bx. So we factor the x. That will be quantity negative a plus b quantity x. And then the constants will be a plus 4b. Now, for these two to be equal, for the equality to hold, their corresponding coefficients must be equal. So in other words, we will compare coefficients. We compare coefficients. So the coefficient of x at the left side is 0 because there is no x term. There is an x term, but the coefficient is 0. Alright? So the coefficient of x at the left side is 0, equal to the coefficient of x at the right side, which is negative a plus b. Then we also compare the constant. Actually, the constant is x to the 0. X to the 0 is 1. So the constant at the left side is 1. And that must equal to the constant at the right, which is a plus 4b. So what we have here are two equations in the unknowns a and b. So we solve for a and b, or we solve for these two equations simultaneously. So it's clear that by adding these two equations, we'll be eliminating a. So we add 0 and 1 is 1, negative a and a is 0, b and 4b is equal to 5b. So that gives us the value of b equal to 1/5. So if b is 1/5, no, substitute it the first equation. If b is 1/5, then a is also equal to 1/5. Right? So we go back to our integral. The integrand 1 over 4 minus 3x minus x squared is equivalent to a over 4 plus x plus b over 1 minus x. Since we have already calculated for the values of a and b, we write there 1/5 over 4 plus x, and then b is also 1/5 over 1 minus x quantity dx. Alright? We then evaluate these two separately. Since we have a linear factor in the denominator, then the formula involved is du over u, and that is 1/5 ln of the absolute value of 4 plus x. Then plus 1/5 dx over 1 minus x. Take note, 1 minus x, the derivative is negative 1. So it should be negative ln of the absolute value of 1 minus x plus c. So you can see that we can factor 1/5. That will be ln absolute value of 4 plus x minus ln absolute value of 1 minus x plus c. And we can further polish our final answer by combining these two ln's. The difference of two ln's is equivalent to the ln of their quotient. So ln of 4 plus x over 1 minus x plus c. Okay? Now, there's another way. There's an alternate solution for values of a and b. No? So instead of comparing coefficients, we can substitute values to x in order to solve for the constants. So what we have is, let us go back to this portion. So we have 1 equal to a times 1 minus x plus b times 4 plus x. We substitute a value to x that will make the factor 0. So let's start with 4 plus x. To make the factor 4 plus x equal to 0, we can set our x equal to negative 4. Okay? So what will happen? We have 1 equal to negative 4 minus negative 4 negative 4. 1 minus negative 4 is positive 5. So it gives us 5a, hence a is 1/5. How about 1 minus x? To make the factor 1 minus x equal to 0, we can set our x to 1. So 1 is equal to 1 minus 1, that will be 0. 4 plus 1 is 5. That gives me 5b. So 1 is equal to 5b, or b equal to 1/5. And these values are exactly the same as the values of a and b we had using the comparing coefficients method. Using the previous method of comparing the coefficients, we were able to get the same set of answers. So it's up to you to decide as to which method would you prefer, either comparing coefficients or by substitution. We take on another example. We take on the integral of dx, but let us put an x. Let us put a function in the numerator, say x plus 2 quantity dx all over 2x cubed plus, let me see, 7x squared plus 3x. There. We isolate our integrand just like what we did earlier. So isolate the integrand. When we speak of the integrand, it refers to the function without the differential. So x plus 2 all over 2x cubed plus 7x squared plus 3x. X plus 2. We can factor x first in the denominator. That will be 2x squared plus 7x plus 3. And 2x squared plus 7x plus 3 is further factorable into what? 2x plus 1. And then what else? 1 plus 3. Or x plus 3. I think it is x plus 3. Let us check. 2x times x is 2x squared. X and 6x is 7x. 1 times 3 is 3. Okay. So we see that there are 3 linear factors involved. Hence, there will be 3 partial fractions. No? X is a linear factor, so it deserves 1 partial fraction. And then 2x plus 1 is another. And still another is x plus 3. So we have to solve for the values of a, b, and c. Just like what we did earlier, we combine these 3 with the same denominator. So that becomes a 2x plus 1 times x plus 3 plus b x plus 3 plus cx. Okay, let me adjust this. So cx times 2x plus 1. There. Let's move this a little. Okay. So we can cancel the denominators. They are the same. They are equal, so they are cancelable. So what remains at the left side is x plus 2 x plus 2 equal to a 2x plus 1 times x plus 3 plus bx x plus 3 and cx 2x plus 1. Let us use the substitution method. Say x is equal to, we get rid of x, so let x be equal to 0 to get rid of the first factor. So all x's will be 0. So 0 plus 2 is 2. 2 times 0 plus 1 is 1. 0 plus 3 is 3. So 1 times 3 is 3 times a, or 3a. bx, cx are both 0. So our a is 2 all over 3. Okay, how about the factor 2x plus 1? We let x be equal to negative 1/2. So all x's change to negative 1/2. Negative 1/2 plus 2 is 3/2. Those with factors 2x plus 1 will be 0. Okay, so a times 2x plus 1, cx times 2x plus 1, they will both be 0. So b times x, so that will be negative 1/2. Then negative 1/2 plus 3 is 5/2. So negative 1/2 times 5/2 is negative 5/4 b. Negative 5/4 b. So the value of b will be equal to, okay, the value of b will be equal to, the 2 will cancel, negative 6 over 5. Negative 6 over 5. Okay. So we check. Negative 1/2 plus 2 is positive 3/2. Negative 1/2 plus 3 is 5/2 times negative 1/2 is negative 5/4. So we cancel the 2. 6 over 5 negative. Alright, next, to get rid of the factor x plus 3, let x be equal to negative 3. X be equal to negative 3. So negative 3 plus 2 is negative 1. X plus 3 will be 0. So that leaves us the last term. C times negative 1. 2 times negative 1 is negative 2 plus 1 is negative 1. Negative 1 times negative 1 is positive 1c. So our c is negative 1. Okay? So we go back to our integral and write this as the integral of a 2/3 over x plus b, which is negative 6 over 5 rather, over 2x plus 1, and c is negative 1 all over x plus 3 quantity dx. We integrate these three separately. So 2/3 dx over x is of course ln of the absolute value of x minus 6 pips. The integral of dx over 2x plus 1, take note, the derivative of 2x plus 1 is 2. So that will be 1/2 ln absolute value of 2x plus 1 minus dx over x plus 3 is ln of the absolute value of x plus 3 plus c. So that is 2/3 ln absolute value of x minus 6 over 10 is 3 over 5 ln of 2x plus 1 minus ln of x plus 3 plus c. You can simplify your answer by combining these 3 as 1 ln. So we can factor 1 over 15. Alright? Factoring 1 over 15, 15 divided by 3 is 5 times 2, that will be 10 ln of x. Minus 15 divided by 5 is 3 times 3 is 9 ln absolute value of 2x plus 1 minus 15 ln of absolute value of x plus 3 plus c. And all these coefficients, all these coefficients, 10, 9, and 15, will become the exponents of the functions. So 1 over 15 ln of x raised to 10 minus ln of 2x plus 1 raised to the power of 9 minus ln of, let us write there the absolute value of x plus 3 raised to the power of 15 plus c. And let us do that also for 2x plus 1 to the 9. It must be the absolute value. 2x plus 1 raised to the power of 9. And these 3 ln's are then combined. We then combine these 3. So that will be ln, the grand ln is ln of x raised to 10 all over, because of the negative sign, 2x plus 1 raised to 9, and x plus 3 raised to 15. Let us write the absolute value plus c. Okay? One final example. Say we have x squared minus, let me see, x squared minus 3x plus 1 dx all over x cubed minus 2x minus 5x. Okay, make it 2x squared minus 5x plus 6. So we examine the denominator, and by inspection, it seems that we cannot disintegrate this or break this down into 3 linear factors. So what we do is we apply synthetic division by trial and error to find out whether there are linear factors, or whether this cubic can be converted into a product of linear factors. So let us have a space to work on. X cubed minus 2x squared minus 5x plus 6. Using synthetic division, we pluck out all the coefficients, 1, negative 2, negative 5, and 6. And then we determine the factors of the constant 6. So the factors of 6 are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. So these are the factors. These are the candidates. So by trial and error, we try on this one by one. So if we're lucky enough, we can immediately get the factors. So we can start with 1. So we bring down 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times 1 is negative 1. Negative 5 and negative 1 is negative 6. Negative 6 times 1 is negative 6. And 6 minus 6 is 0. So that's it. So we're lucky enough to get the root. Actually, 1 is the root. And the factor corresponding to this is x minus 1. Why? If it is the root of x cubed minus 2x squared minus 5x plus 6 equal to 0, that means that x is equal to 1, which is equivalent to x minus 1. So x minus 1 is the factor, or is one of the factors. And these constants become the constants or the coefficients of the function or of the polynomial 1 degree less. So if it's x cubed, this will be the coefficient of x squared, x, and the constant. So this is equivalent to x squared minus x minus 6. We can apply a new synthetic division to the constants 1, negative 1, negative 6. But x squared minus 6x minus 6 corresponding to that polynomial, by inspection, the factors are x minus 3 and x plus 2. Okay? So x minus 3 times x plus 2 is x squared, minus 3x plus 2 is negative x, and negative 3 times 2 is negative 6. So now we know that x cubed minus 2x squared minus 5x plus 6 is equal to the product of x minus 1, x minus 3, and x plus 2. So these are the three linear factors. These are the three linear factors of the denominator. So we can write this now as the integral of, there will be three partial fractions, a over x minus 1 plus b over x minus 3 and c all over x plus 2 quantity dx. So we just have to solve for the values of a, b, and c. So that will be x squared minus 3x plus 1 over x cubed minus 2x squared minus 5x plus 6 is equal to a over x minus 1 plus b over x minus 3 plus c all over x plus 2. Equivalently, a times x minus 3 x plus 2 plus b x minus 1 x plus 2 and c x minus 1 x minus 3 equal to x squared minus 3x plus 1. So we can solve for the values of a, b, and c. Okay, so that is a work for you. So this is a job for you. You calculate for the values of a, b, and c. So once you have calculated, you just plug in those values to a, b, and c here. Then you integrate. So whatever the values of a, b, and c are, your answer here will be a ln of x minus 1 plus b ln of x minus 3 plus c ln of x plus 2 plus the constant c. Okay, so it's a job for you to solve for the values of a, b, and c using any appropriate method or any method which you prefer. Alright, so as an exercise, you work on the following integrals. So the integral of 3x plus 2 all over 9x cubed plus 8x squared minus x minus 2 dx. And number 2, t squared minus 5 dt all over 4t cubed plus 8t squared minus 15t minus 9.